Oh, hey. Sorry, I didn't see you there. Just trying to solve my Rubik's Cube here. Alrighty, so you go left, right, you want the white here. Ugh, I can't do this. You know what? Let's see if a computer program can do this. Hello, my name is JP Harms, and I am a computer science graduate student at the University of Louisville in the JB Speed School of Engineering. This is my final research project presentation on the evolution of NP-complete problems studying formally in the Rubik's Cube puzzle. Let's jump right in. First off, I'm going to give a brief history and time of the Rubik's Cube. In 1975, Erno Rubik was the one who was granted the patent for the 3x3 Rubik's Cube, which was actually called the Magic Cube. In 1982, one of the major milestones is when the first ever Rubik's Cube World Championship was hosted. Speed cubing is basically taking a cube and solving it in an amazing amount of time, much faster than the average human being can do. In fact, you'd think they were robots. In 2004, the World Cube Association was founded. The World Cube Association is an association that basically guidelines and holds all the regulations for the speed cubing competitions that are held. To this day, they are still holding speed cubing competitions with young Rubik's Cube athletes solving Rubik's Cubes in an insanely fast time. Wow, look at all these cubes. You can see here there's a ton of different types of Rubik's Cubes out there. For instance, we have the 2x2x2 cube known as the pocket cube. That is your cube in the top left corner where it's circled in red. In the bottom left corner, you'll see the average Joe Rubik's Cube, which is the normal 3x3 cube, which you've probably seen many of. Not known to most people, there's plenty of other cubes as well. There's the 4x4x4 cube shown in the middle. In the top right corner, there's the 5x5x5 cube. This cube is known as the Professor's Cube. I'm not sure why it's called the Professor's Cube, but that's what it's called. In the middle, you'll see a pillow-looking cube with a V on it. That's known as the V cube. The V cube is a 7x7x7 cube. I can only imagine how many permutations of that scrambled cube there is. In the bottom right-hand corner, you'll see the Scoob cube. Not named for Scooby-Doo. In fact, this is actually just based off its triangularly shaped corners, which are used to solve the cube. In the middle, you'll see the weird-looking cube that kind of looks like it's from the Willy Wonka factory. That's known as the Megaminx. It is a dodecahedron-shaped cube puzzle. Of these cubes, our project is focusing on cubes with the circled in red. The Pocket Cube, the Rubik's Cube, the Professor's Cube, and the V Cube. Now, let's describe a little bit about what our project actually is. So this project is utilizing a computer to solve the Rubik's Cube. Instead of a human solve, we're going to take a computer and we're going to attempt to apply a thing known as a genetic algorithm, which we'll explain later in this presentation, and the wisdom of crowds method in order to solve the Rubik's Cube. This next slide is showing a couple more cubes. You can see there's this 3D printed cube, which currently is the largest cube in the entire world. It's 33 by 33 by 33 size. That's a huge cube. In the top right hand corner, you'll see the mirror cube. It looks similar to the 3x3x3 Rubik's Cube, except that it has different dimensions for its cubes. In the bottom right hand corner, you're just going to see one big freaking cube. Man, I wish I had that in my backyard. Okay, now let's talk about what an NP-complete problem is. An NP-complete problem is basically a problem that its solve time, the algorithm solve time, is expanded upon polynomially over time based off the size of the input. So take it as in you have a problem that's based off only 10 choices, it may only take a few milliseconds to solve. As those choices go up, an NP-complete problem will take a ginormous amount of time, thus leading to having to have your computer on for several hours or days to solve. The NP-complete problem of the Rubik's Cube is an n by n by n cube, where n is known as the number of tiles per face. Thus, the 2x2x2, 3x3x3, 5x5x5, and 7x7x7. You'll see in the results of this code that it is proven that this is an NP-complete problem because the algorithm time taken to just solve the cube grows polynomially. A cube is known by 6 faces. There's the red face, the the green face, the orange face, the yellow face, the blue face, and the white face. It's made of 3 different types of cubies. There's the corner cubies, the edge cubies, and the center cubies. For a 3x3x3 Rubik's Cube, the corners have 3 face tiles, all have different colors, 2 edge tiles, and then 1 center tile. The center tiles stay in the same spot for this cube. It helps you understand which colors should be in which face. So, for example, as well, with the Rubik's Cube, there are 26 cubies in total, 6 center cubies, 8 corner cubies, and 12 edge cubies. Okay, now let's talk about how we actually move the cube. So, when you have a Rubik's Cube, a 3x3x3 cube, you can make 6 different types of turns on that cube. Since there are 6 faces, you can move each of those faces. You can move a face clockwise, you can move a face counterclockwise. The counterclockwise moves are denoted by the asterisk. On the left side of the screen, you'll see the shared block. The shared block shows which types of turns you can make in the 3x3x3 cube. Notably, these turns are also available in the Professor's Cube, the V Cube, and the Pocket Cube. Now, in the bottom right-hand corner of the screen, you'll see the cubes that are specific just to the Professor's Cube and the V Cube. These moves include moves for the inner rings of the cube. So you'll see an F_2, that is the first inner ring from the front face. Going down, you'll see the first inner ring for all of these faces. You'll also notice there's a horizontal inner ring. For the 5x5x5 cube, that is a specific turn just for that cube. Now, particularly to only just the V cube, you'll see in the top right-hand corner those moves. The V cube is special because it's 7x7x7. That means there's also a second inner ring, a third inner ring on most of the faces of the cube. Okay, since we've talked enough about how to actually show the moves in a computer program, let's talk a little bit about the human solutions. So, the most typical solution for speed cubers is the 5 steps. This is a beginner's algorithm that is used in order to solve a Rubik's Cube. They involve the following steps. The first step, complete the first layer across. The second step, you complete the first layer corners. The third step, you complete the second layer. The fourth step, you complete the third layer across. And the fifth step, you complete the third layer corners. In the next slide, I'll show you a picture of what that looks like. In the right corner of the screen, you'll notice the World Cube Association current fastest solves are listed. For the Pocket Cube, it was solved in 0.49 seconds. That is insanely fast. For the 3x3x3 cube, 3.47 seconds, and you'll see how it goes up and up as the cube gets larger. Okay, in the next slide, we're going to show how you actually solve the cube in the human form. So you'll see that first step in the bottom left-hand corner, completing the first layer cross. You'll see on the top, the cross is noted by that white cross on the top of the cube. Then you'll see the second step is solving the corners of the cube. Note, this also means the colors on the side of those cubes have to be solved as well. The third step is to solve the second layer of the cube. You'll see that that layer is solved below. Notice that this cube was actually flipped over. The white cube is now on the bottom. Now we're going to solve the third layer across. You'll see on the top that it's solving it in yellow right there. And finally, we're going to solve the final corners of the cube. Okie dokie, now we're going to talk about our approach that we did in this experiment. So as we stated earlier, this is an experiment utilizing genetic algorithms and the wisdom of crowds. The genetic algorithm is based on the following premise. You start with a population of random solutions. From those random solutions, you need to define a fitness factor. The fitness factor is basically, how well done is that solution. Then you need to define 2 strong parents from that. You choose them based off their fitness, so therefore people with higher fitness has a better chance of being selected as a parent. Those 2 parents are mixed together to create offspring solutions. From those offspring solutions, you continue this process over and over. So you find another 2 strong parents, create some offspring, put them in the offspring population, find 2 strong parents, create some offspring, yada, yada, yada. You basically perform that until the offspring population size equals the parent population size. That completes 1 generation. In the code, you actually specify how many generations you want to run. The end of the genetic algorithm actually ends with a high quality solution. So you typically do generations until you want a satisfactory result. Now, the wisdom of crowds method is an addition to the genetic algorithm. It utilizes those high quality solutions that the genetic algorithm has created, and it wants to create one solution from that. The wisdom of crowds method is based on the fact that you take a crowd of people, particularly experts in a field. They all provide their own individual solution to a problem, and you aggregate those solutions, and you can actually create a better solution to that problem. It is not always applicable to everything, but we're hoping that'll be applicable to the Rubik's Cube. Now we're going to define the solved state of a Rubik's Cube. You'll see on the right side of the screen the solved configuration of the Rubik's Cube. You can see all the colors are in the correct spot, the correct orientation in the cube. So the solved state definition for the computer program is basically it iterates through all of the different faces and makes sure that each face has the correct color in it. We've also defined that this is the fitness factor for a genetic algorithm. The fitness factor details how many tiles have the correct color in them. So this fitness factor may range for a 3x3x3 cube from 1 to approximately 9 times 6, which is 54. So obviously a solved cube would have 54 fitness. Also in our program, we are tracking the individual tiles per face. So therefore, how many yellow faces are in the correct color, how many red faces are, and continued. Alrighty, here are our problem parameters. Our cube sizes, we've already told you, the pocket cube, the Rubik's Cube, the professor's cube, and the V cube. Our population size for our genetic algorithm is decided to be 50. We're going to be doing 40 runs because we figured that is enough to get an accurate amount of experts. Our number of generations for each of the tests we did was 1,000 generations. This was chosen for multiple reasons. In order to hopefully define a good end solution for the genetic algorithms to give a good quality solution, and also because of the computation time. As the number of generations keeps going, the computation takes exponentially longer, and with a short limited time to actually pull results, you may only be able to get a certain number of tests completed. Our chromosome for this genetic algorithm and the step length is decided to be 50. Alrighty, let's talk about the engines that drive the genetic algorithm. So you might have wondered, when you're creating offspring, how are you actually going to combine the parents' solutions together? So those are done using a crossover method. The mutation is a function of our algorithm that allows us to make a slight change to an offspring. This allows more randomness and variation in our genetic algorithm. The crossover methods that were chosen in this genetic algorithm are the total colors correct and the single face colors correct crossover. The mutations that were chosen are the random injection and the swapped mutation. The total colors correct crossover method that's used in this genetic algorithm operates on the two following premises: the finding a match premise and the creating offspring premise. In the finding a match premise, two parents are first selected for mating. Then the solution steps from each of those parents is performed on a scrambled cube step by step. At each of those steps, the total number of correct colors is calculated and tabulated. Then you compare both of those parents and you want to find where the matching point is. The point in each cube with the most similar number of total correct colors is measured, and that's the matching point. That matching point is very, very important in the creating offspring portion. When you create the offspring, you actually take the first parent up to that matching point. You add all the steps to the offspring chromosome. Then from the second parent, you find its matching point and you add the steps from that. That creates one chromosome. Now let's say there's not enough steps are actually in that chromosome. Then we'll add some random steps to the solution to meet the required length of 50 steps. In the single phase colors correct, it's almost exactly identical to the total colors correct method, except that now we're actually calculating the total number of correct colors per each face instead of for the total cube. This gives us a much more defined version of a matching cube. Then when you create offspring, it's pretty much in the exact same fashion as the total colors correct method. Here are two mutations. The random injection mutation finds 3 randomized steps in the offspring solution and then it replaces them with a randomly generated move. The swap mutation replaces the entire offspring with the new randomized solution. Wisdom of crowds. For us to be able to do a wisdom of crowds, we have to aggregate the expert solutions. So from the genetic algorithms, we pull out a panel of experts from them. Those panel of experts are iterated step by step to create an aggregation table. This aggregation table is defined by the amount of rows and the columns. The amount of rows is equal to the step length or chromosome length that's defined, which in this implementation is 50 steps. The columns represent every move type for the cube. So as you can tell, for each different cube, you'll have more or less move types. Now, for generating the solution of the wisdom of crowds, you iterate through each row and you tabulate the sum of moves per step in the solution. You generate the final solution by going each of those rows and finding the local maximum at each one and adding step by step to the wisdom of crowds solution. Alrighty, here's our ground rules for our experiments. So we are doing a total of 16 different tests. That means there's 4 tests per each of the cube configurations we're doing. The alternating factor for each of these tests is what crossover type and mutation type is chosen. Our data in our experiment is from a randomly generated set of cube moves. As shown in the bottom right hand corner, here's an example. A right turn that's clockwise, a 90-degree left turn that's counterclockwise, a interface on the right face clockwise, and so on and so on. Here's a snapshot of the GUI that we created in Qt Creator. You'll see here that the cube is portrayed in a 2-dimensional form. The bottom right hand corner has all of our data that we need for our results. The bottom left hand corner creates a couple of very important graphs, including an improvement curve and an algorithm time curve. The top left corner are our buttons that we use to actually create new cubes and scramble it, and define what type of cube size we use. The parameters for our cube are located in the center of the screen. Here are some of our results. Our algorithm time results are shown below. Our initial observation from this algorithm time results shows that the single phase colors correct crossover and the random injection mutation combined together yielded the best fitness out of all the 4 types. Though, it should be noted that this required a larger computational time requirement. Here are some of our improvement curves. You'll see all the improvement curves for all of our different cube types. A couple of observations we made from this data are that the pocket cube and the Rubik's cube showed an improvement in their fitness. The professor cube and the view cube, albeit, did not show as much of an improvement, whereas the view cube actually was much more scattered. This is most likely due to the fact that the view cube has 7x7x7 configuration. Therefore, it probably requires a lot more than 1,000 generations to come up with a solved solution. Here are some of our algorithm time curves that we also generated in our results. You'll see one for each cube. All of these show a pretty scattered algorithm time, which I think is very good for our results because in our program we reutilize a lot of variables and members in the source code in order to keep the actual code very light in our processor. Here are some of the sample genetic algorithm solutions that were provided in our results. You'll see the actual solution that was at the end of the genetic algorithm, the best version for each cube. Here is a table for our solution results for just the genetic algorithm and the genetic algorithm and the wisdom of crowds method combined. The columns defined in this table are set by the actual ratio. So you'll see that for the pocket cube, there were 0 correct faces from optimum. This means that the actual pocket cube was solved by the genetic algorithm. You'll see the Rubik's cube is about 37% off from the actual correct faces. So I'd wager that means there was probably about 40 solved faces for the 54 that there should have been. The professor cube was about 50% off, and the view cube was about 67% off. You may think that this is a lot off, but this is most likely due to the fact that not enough generations are moved, and it also shows that improvements can be made in the crossover methods. Now, for the genetic algorithm and wisdom of crowds, you'll see that there's a lot more variation. These solutions were actually a much more off from the optimum solution. You'll see 58% off was just for the pocket cube, 62% off for the Rubik's cube, and on and on. Here are some observations from those charts. We definitely have noticed that the genetic algorithm by itself produces a much better result than the combined hybrid solution. The genetic algorithm did not always reach an optimal solution, but it still provided good results. We also noticed that as the cube size grew larger, the amount of correct faces decreased in percentage. We also noticed that the wisdom of crowds method performed very poorly. We believe this is due to the fact that the wisdom of crowds method that was chosen in this experiment may not have been the best representation of what an actual solution of a Rubik's Cube is. When you solve a Rubik's Cube, you usually solve it in smaller versions of algorithms. So you'll do it maybe 4 steps at a time to solve an actual cubie. The wisdom of crowds method, on the other hand, solves it step by step. That means, sure, you may have found the most optimum step at that point, but that step doesn't always pertain to the optimum step before it, thus causing poor performance. So, what's next? Here are some improvements we should make to our program. We believe that we can definitely probably find a better precise crossover method out there. Another improvement to my program is to also find a much better wisdom of crowds method that could be utilized. We also thought it would be very awesome to model the Rubik's Cube as a 3-dimensional cube rather than a 2-dimensional cube in our GUI. Some future research which might be interesting is to take some of the solutions that were provided by this experiment and actually perform them on a pre-scrambled Rubik's Cube. Here's some final comments and what I believe I learned from this project. I definitely learned a lot about how to visualize an NP-complete problem and implement it within the C++ programming space. I also learned a lot about how to create a GUI and to utilize it for performing repeated experiments. I learned how to utilize my time wisely when running applications that would take a good deal of computational time. I also learned a lot about the software development process. A lot of time should be taken upfront in order to prepare and test your algorithm before your full-out software code implementation is performed. Of course, I definitely learned a great deal about genetic algorithms, wisdom of crowds, and Rubik's Cubes. Here are my references for this presentation. Thank you very much for listening. Alrighty, now I know how to solve the Rubik's Cube. So you do step 1, you complete the first layer across, you do that, you complete the first layer corners. Oh yeah, then you do the second layer. Yep, you gotta do the second layer, that's true. Then you do the third layer across. Yeah, there's a cross right there. Then you gotta do the third layer, the fourth layer, the third layer, you know what? I think I'm gonna have the computer do the dirty work for me. Bye!